This is the preliminary design review of the Pro-S throwable generator for the 2014 fall semester. Our group is composed of 5 undergraduate students of the Electrical Engineering Department at the University of South Florida. Our names are Calvin Likens, Wong Nguyen, Jesse Miner, Neil Camardella, and Van Nguyen. The mobility of portable electronics is limited by their power consumption. We propose a portable throwable generator that harvests kinetic energy to charge a battery. This battery can be removed and used as a backup for portable electronics.
This is a general block diagram of our energy harvesting system. The generator takes energy out of the speed and rotation of the throw and converts it into electricity. This electricity is then smoothed and upconverted to charge the battery pack. This battery can then be used by the user to charge the portable electronics. The Pro-S system has 2 modes, throwable mode and wind turbine mode. In throwable mode, the generator housing will have curved tail fins attached to it. These increase rotational speeds as it flies through the air, allowing users to throw with better accuracy, and it increases the power production of the entire system. As air flows through the open mouth of the generator housing, the turbine blades, which are colored gold in the diagram and are connected directly to the generator shaft, will counter-rotate against the rest of the generator and the generator housing, capturing the energy of the passing air. The fins also create a watertight seal around all electronics and can easily be unscrewed to access the portable power pack. The portable power pack allows users to conveniently charge their electronic devices without carrying around the entire generator system. In wind turbine mode, the tail fins are replaced with a mount which allows the Pro-S system to be attached to a wide variety of objects to serve as a stationary wind turbine when users aren't playing catch or if there's only one person. The clamp can easily be attached to a beach umbrella to catch energy from the breeze or bike handlebars to harvest power on the way to the park. The wind turbine mount also creates a watertight seal around the electronics, so there's no need to worry about bad weather when in use.
The rectifier is divided into 2 stages. First is negative voltage converter, and second stage is anti-diode current barrier. The voltage converter circuit is on the top left of the slide. On the left side of the circuit, BMOS transistor delivers the highest potential at V into node A. On the right side of the circuit, NMOS transistor delivers the low voltage potential to point P. The ability to convert nearly the entire voltage applied at the input and output is the main advantage of the circuit. The voltage drop of the circuit is less than 10 mV. However, the current direction is not controlled, and the current backflow occurs. The circuit cannot be used to charge a storage capacitor.
The BQ25504 is well suited for meeting the special needs of ultra-low power applications. The product is specifically designed to efficiently acquire and manage the microwatts to milliwatts of power generated from a variety of DC sources. The BQ25504 was designed with the flexibility to support a variety of energy storage elements. The availability of the sources from which harvesters extract their energy can often be sporadic or time varying. The design of the BQ25504 starts with the DC to DC boost converter / charger that requires only microwatts of power to begin operating. Once started, the boost converter can efficiently extract power from low voltage output sources. The boost converter can be started with an input voltage as low as 330 millivolts, and once started can continue to harvest energy down to 80 millivolts.
Hi, I'm going to talk about energy storage. We came up with 2 solutions for our energy storage. They are lithium polymer, rechargeable battery, and supercapacitor. We decided to choose lithium polymer rechargeable battery because of its large capacity compared with that of supercapacitor. Looking at the graph on the left, you can see a lithium polymer battery needs to be charged with the constant current. In this case, 1 amp. Um, and at the beginning, the voltage across the battery is very low, around 0.25 volts. And when the voltage reaches 4.2 volts, it will saturate. And in order to keep the voltage the same, the current needs to decrease. When the current decreases like less than 3% of the rated current, um, the battery is fully charged and the charge will terminate. Nowadays, most of the battery has a built-in protecting circuit to prevent the battery from overcharging and a short circuit. Um, for our battery, the maximum capacity is 2000 milliamp hour after fully charged, and the output voltage of our battery is 3.7 volt. And next, my friends, Neil's gonna talk about useful power.
The stored energy of our system will be extracted via a USB port. This will enable compatibility with the majority of portable electronics. A boost converter will be used to boost the 3.7 volt battery output to the 5 volts required by the USB standard.
Our timeline starts at the end fall semester to the spring semester. Before December 15th, order generator, components of rectifier, and boost converter. Then from December 15th to December 29th, we will concentrate on analyzing and studying the characteristics of generator and boost converter. Also designing rectifier circuit. Battery will be ordered, and output configuration will be designed at that time. A month starting from middle of January, generator, rectifier circuits and output configuration will be static, and starting to design the innermost enclosure. Until middle of March, design outer cell and test enclosure will be completed. At the end of March, testing output shell will be done. From the first week of April, the whole system will be tested and modified if needed.
The main risk our product will be facing are impacts. This is pretty obvious because our product is meant to be thrown, so the generator housing needs to be sturdy enough not to break, but flexible enough to absorb impact to protect electronics and users if they get hit with it. Another problem we'll be facing is water, because the product is intended to be used outdoors, and our survey indicates that people are very interested in using it at the beach and other places where contact with water is imminent. So we need to make sure that all the electronics are sufficiently protected and that rough play will not compromise this protection. We handed out about 50 surveys across campus, half around the engineering buildings and the other half in Marshall Student Center. These surveys, in addition to helping us improve our design, provided some useful feedback on customer interest. The vast majority of people surveyed were somewhat too interested in our product, with only a couple people describing themselves as not interested. The survey also showed that people wanted to use our product in many different places, proving its flexibility. Our product has many market risks, including about all balls and sports equipment, rechargeable battery packs, and portable solar and wind chargers. But even though our product has many market risks, we believe our product has an interesting take on a solution to a common problem.
Listed below are all the courses relevant to USF's electrical engineering curriculum. The ones highlighted are the courses that our group felt helped out the most in the concept and design of our product. The courses include but are not limited to Electrical Systems 1 and 2, Lab 1, Electronics 1, and Lab 2. In summary, we hope to design a system that combines the fun of a game with the practicality of a portable charger.